Hello everybody. Today we will see the behavior of resistor inductor and resistance capacitance connected in series in AC circuits. Yesterday's session we saw the individual behavior of the individual elements in single phase AC circuits. So today we will be doing the series combination of resistor inductor and resistor capacitors in AC circuits. A simple example for a series RL circuit, that is resistor inductor circuit, is a practical inductor. In the formation of inductor, we take a straight conductor and we wound it in the form of a coil, or a straight conductor also can have an inductance when it is carrying an alternating current. Along with resistance, it will have an inductance. So a practical inductor, we can say, possesses inductance and resistance in series. Analysis of RL, R and L in series is equivalent to analysis of a circuit containing a practical inductor. So for this analysis, we are considering a series combination of resistor and inductor connected across a alternating voltage source, as I have shown in the figure. Now our aim is to find out the steady state response for the given applied voltage V. The reference polarity of the voltage V is shown by means of an arrow. You can see here, this is the arrow represents the direction of the current given by the voltage source, or you can say the tip of the arrow represents the higher potential point plus, and the tail of the arrow here represents the lower potential point or minus terminal. The reference polarity of V, represented by this arrow, causes a current I to come out of the voltage source and flow into the circuit. So this current which is flowing through the resistor and inductor will give us a voltage drop of VR and voltage drop of VL as the voltage drops across resistance and inductance respectively. Now if you see the current, I have represented the current there as IR and IL. Now as the elements are connected in series here, for this circuit we will have, see, this is what I have represented as IR. I can have a series combination in any way. I can have inductance first and then resistance. Any fashion I can connect these two. The current what is flowing through the resistor R after coming out in this circuit is flowing through the inductance L. So VR, it is the RMS value of the voltage drop across the resistor, and VL, it is the RMS value of the voltage drop across the inductor. Both these voltage drops are because of the same current which is passing through these two elements. As the two elements are connected in series, they will carry the same current. So for this circuit, if I apply Kirchhoff's voltage law, we get I is equal to IR is equal to IL. And in the analysis of this circuit, we apply Kirchhoff's voltage law also. Here we have a closed loop, okay, there is a closed loop here. Now the polarity of the voltage drops is represented by plus sign and minus sign across each elements. So the current in the circuit element, this is a passive element, will enter at the positive terminal and comes out of the negative terminal. Similarly, the inductance is also a passive element, therefore the current IL or I in the inductor is entering at the positive terminal and leaving that at the negative terminal. Whereas the voltage source is an active one, therefore the tip of the arrow, when I represent it with a positive terminal, in the active source the current will come out of the positive terminal and will enter back to the source through the negative terminal. Now as I told you here, depending on the elements connection, I will be using both the laws, okay, Kirchhoff's current law as well as Kirchhoff's voltage law for the analysis of the network. So the Kirchhoff's current law will give you the relationship between the elements currents to the current given by the source, and the voltage law will give us a relationship between the applied voltage to the combination and the respective voltage drops across the elements. So this slide tells you that we use Kirchhoff's voltage law for the analysis. KVL is a basic law, Therefore, it is applicable for all the circuits at all instants, whether the circuit is DC or AC, it does not matter, it is applicable at all instants to all the circuits. In an AC circuit, the voltage and currents are phasors, therefore, we do the phasor analysis by treating the voltage and current as phasors. For the analysis, we need to draw a phasor diagram which relates the vectorial position of the voltages and currents in the network for the various elements. Now, let us see how to draw the phasor diagram. To draw the phasor diagram, I will be taking here the series RL circuit as a reference one. Okay? With respect to this circuit, what all the steps I have given in my presentation will tell you how to draw the phasor diagram for a series RL circuit. The same procedure with a small changes, okay, in the vector positions is applicable for other circuits also. Now, first of all, we do in the first step, I will be marking the polarity of the voltage source. Okay, I am just mark the polarity like this, the arrow, we use the arrow to represent the polarity of the source. Okay, or I can also represent either by taking a plus sign and minus sign. When I put a plus sign, I have given you an arrow here. So, corresponding to the arrow here, when I give a plus sign, the tip of the arrow I will be marking positive. So, automatically the other end of the arrow, what represents the tail, that will be the negative terminal. Okay? And this arrow, it also gives us the current direction given by the source. So, that current direction I marked it here, I. So, in the step 2, I am just marking the voltage across the current through each individual component of the circuit, that is the current must enter the plus mark terminal of the component because it is a passive element. Okay. So, VR and IR, these are the current, IR is the current and VR is the voltage across the resistance, and IL is the current in the inductor, VL is the voltage drop across the inductor. If I show these diagrams, it is very easy to write down the phasor diagram. I have a resistor and inductor. So, to this combination I am connecting a voltage source. This is a AC alternating voltage source with a RMS value of V volts. I have marked the arrow here. So, if I do not want to mark arrow, I can mark positive negatives. So, the current given by the source I is like this. So, the current into the resistor will enter here, it will come out here, and the same current as inductor current will flow through the inductance L, R is the resistance. This current flow of IR through the resistance is giving us a voltage of VR, and it is giving us a voltage drop of VL across the inductor. So, this is the way I can mark the polarity of the voltage drops and the current directions in the elements. Now, the next step is to draw the phasor diagram for the individual components. In the last session, I gave you the vector diagrams for resistor, inductor and capacitor separately, treating each element as a separate entity, and I applied a voltage source of V volts to each element separately, and I have given you the relationship between the voltage and current in the form of a phasor or phasor diagram. See, for a resistor, the current is always in phase with the voltage. Therefore, I draw for a resistor, the phasor diagram will be the voltage VR across the resistor and the current IR through the resistor, both are in phase. That is, the phase angle difference is 0 for that. I can have whether VR larger or IR larger. Generally, if R is greater than 1 in magnitude, any value of the current I will give you a voltage drop whose magnitude will be larger than the current magnitude. See, on the board I have written VR is greater than IR, but on my slide it is showing that IR has a larger length than VR. Anything is okay, no problem. Okay. Then to draw the current, I am taking the phase angle between the voltage and current as 0. This is true for all resistors, okay, whatever the value of resistance may be. See, the next element what we have is an inductor. inductor here. Now, if I take the voltage drop across the inductor as reference, that is VL, okay, the current in the inductor will lag behind the voltage by an angle of 90 degrees. So, these are the two phasor diagrams what I have drawn for the individual elements of the series RL circuit. Okay. So, for the first case I have taken the resistor case, I have taken VR as reference, and for the inductor I have taken its voltage drop VL as reference. So, the angular difference what I have between voltage and current in the inductor is 90 degrees. Now, if you see the circuit, actually what you have, the resistor and inductor, okay, both are connected in series. So, for a series connection we have the common parameter as the current. So, to complete the phasor diagram I need to superimpose all the individual phasor diagrams for the circuit by recognizing the common reference or the common phasor among them. Okay. Now, in the series circuit the common reference or common phasor will be the current flowing through that, because in a series circuit any element will carry the same current. So, for this circuit we have IR is equal to IL. So, I need to combine these two individual phasor diagrams in such a way that current IR and IL are common to the circuit. They are common to the circuit. You can see here IR and IL, these two are common. So, I have drawn here two separate circuit phasor diagrams. Now, I need to combine these two to give us a single phasor diagram for the circuit. Okay. Here I have taken IR already along the reference, okay. By nature of the resistor I get like this. Now, I want this IL also to be along the reference, therefore, I need to rotate the inductor phasor diagram in the counterclockwise direction by 90 degrees, so that I will be getting the current vector as the reference and the voltage vector will be coming along the positive imaginary axis. Okay. So, this is 90 degrees. So, I will get VL here. Now, it is possible for me to combine these two phasor diagrams. So, while combining these two, as I told you, I need to take the common phasor as a reference. Therefore, I write here IR is equals to IL is equals to I, and the voltage VR is along the reference, okay, and the voltage VL is along the imaginary axis at an angle of 90. So, adding these two voltages I will be getting, see, to add the voltages I need to draw the VL from the tip of VR, okay, without changing the direction of that voltage. Fine. So, the dotted line is the redrawn position for VL. So, adding these two I will be getting the total voltage V here. So, in finding out the total voltage I am using Kirchhoff's voltage law for the circuit. So, as per the Kirchhoff voltage law, when I move from this point to this point, it is a potential rise. So, this is a potential drop, this is also a potential drop. Therefore, sum of the potential drops in a closed loop is equal to the potential rise. So, that is what Kirchhoff's voltage law. So, I am getting, as per the Kirchhoff's voltage law, the total voltage applied across the combination V is the vector sum of VL and VR. So, the angle what you have between the V and the reference axis, I can call this as theta. It is the angle between the voltage applied and the total current drawn by the circuit. So, therefore, this angle I can call it as the power factor angle for an RL circuit. RL series circuit it is. So, you can see here in the triangle, if I represent the triangle by letters O, A and B, okay, O, A and B, what I have is, I have a right angle triangle. OAB is a right angle triangle in which OA is a voltage drop across the resistor, which will be always in phase with the current, and VL will be the voltage drop across the inductor, which will lead the current by 90 as per this diagram. So, the resultant voltage is V. Therefore, this OAB I can call it as the voltage triangle for the series RLC circuit. Now I can see from the using complex algebra, we can write down the circuit like this. The total voltage V is equals to VR, this is along the reference, okay, and then VR is also equals to I times R, like this, and then the voltage drop across the inductor, when I write, sorry, this is not VR, it is simply VR, okay, no V is there here. VL, it is equals to J times IXL, this is what we have saw yesterday, okay, I times JXL, or it is J I omega L also I can write. So the total voltage, which is the vector addition of VR and VL, all the vectors are represented like this with a small arrow over them, okay. I have not represented that notation in the slides, but we have to treat that VR and VL what I have given in this equation, in the last equation, you need to treat them as vectors. So now if I substitute the expression for VR as I multiplied by R plus J I XL, I can take out I as a common factor, I can write R plus J XL, okay. Now let us see, here I define for the series RL circuit, the term R plus JXL, we call it as a complex impedance, okay. Why it is complex? Because it has a real part as well as an imaginary part, okay. The real part of the impedance is the resistance, and reactive part of the impedance is called reactance, or the imaginary part of the impedance is called as reactance. Now this reactance is because of the inductance L, therefore I call the reactance as inductive reactance. On the slide I have simply represented it as an X, but I can also use a suffix of XL. Even if you do not write that XL suffix, it is understood, because whenever you have a plus sign between the resistor and the inductor, that is the reactance term, okay, it is understood that the complex impedance is because of the inductance in the circuit, okay. So for this series RL circuit, if I represent R plus JXL as Z, as I have shown in the previous slide, I can write this as I into Z. Z, as for this, can also be written as ratio of two complex numbers V upon I, okay. And see here, V upon I can write it as R plus JXL, or simply R plus JX, whatever you want you can write here, okay, JX. Now if I see this triangle here, I just draw the triangle separately, OAB, OAB here, the same triangle what I have shown I am taking. This is what we have, OA is VR, which is I times R, and AB is VL, which is I times XL, and OB, which is V, this is equals to I times Z, and this angle is theta. You can see in this triangle, all the three sides has a common term, current. I can cancel the current in all the three terms. Definitely there will be decrease in the length of each side, but the angles of the triangle will not alter, okay. So when I remove the current from all the three sides, I will be getting another triangle called O. I can still call them as OAB terminals. The angle still remains theta. The base of the triangle becomes resistance, height of the triangle becomes inductance, and the hypotenuse will give us the impedance Z. So this triangle OAB, I can call this as impedance triangle. And this triangle what you have, I can call it as voltage triangle, because all the three sides here they represent the voltage. Okay. This is an impedance triangle and this is the voltage triangle. Now you can see here, when you take a right angle triangle here, I can say the impedance Z is equals to square root of R square plus XL square. That is because this is a right angle triangle. I can apply Pythagoras theorem to this triangle to write down an impedance expression in terms of resistance and inductive reactance. You can see, as per the Pythagoras principle, I have Z is equals to square root of R square plus XL square, or simply you can write R square plus X square. Okay. Since in this triangle, first I know this R and XL for a given RL circuit, then I can have the angle of the impedance theta with respect to the reference is tan inverse XL, that is opposite side divided by the base of the triangle. Therefore, this impedance, which is a complex number, can be written as a magnitude of Z and at an angle of theta. Theta is positive here because this impedance triangle what you have, it is in the first quadrant of the coordinate system. So, this Z will be of magnitude R square plus X square, angle will be tan inverse X by R or XL by R, you can write X by R only you take. Okay. So, we can write like this. This is the form of writing the representing the impedance in complex form. Okay. This is actually the complex form, Z is equal to R plus JXL. Okay. Then I write here R plus JX. Okay. This is called as rectangular form and I call this as a polar form. I can convert from rectangular to polar form using this relationship. Z magnitude is equals to square root of R square plus XL square, magnitude is this. Okay. Angle theta is equal to this value. Okay. This is from rectangular form, I call this as a polar form. Now here this is rectangular form. For certain applications, for certain analysis, when the complex circuits are given, I will be using rectangular form of representing the impedance. For certain analysis, I will be using this impedance in the polar form, that is magnitude and angle form. Given the impedance in the magnitude and angle form, it is possible for us to convert into the complex, that is rectangular form here, because I know what is the length of this hypotenuse and at what angle it is there. Simply resolving that into two components, a horizontal component and a vertical component, I can write the given Z in the polar form to rectangular form by using the expression R is equals to Z cos theta and X is equal to Z sin theta. Okay. R is equal to Z cos theta, X is equal to Z sin theta. Since the sin theta component is always along the vertical axis in the coordinate system, whenever you write Z as a complex number, you should write it as R is equal to Z cos theta plus you should put immediately one letter J here to represent that the reactance is along the imaginary axis. Therefore, it becomes Z sin theta, J Z sin theta. This form also I can convert. Okay. So, given the polar form, I can convert the impedance into rectangular form like this, or given the rectangular form, I can convert into polar form. Okay. We can also use calculators. The scientific calculators are very easy to operate and they give us very easy conversion techniques. Okay. So, this tells about the impedance triangle. Now, here I have taken in this slide what I have shown. I have shown here voltage phasor as reference. When you take the voltage phasor as reference, because that is the what I am doing here, I know the resistor and inductor, but I do not know how much current is flowing through this, but the current is a common parameter. Therefore, in drawing the phasor diagram, I have taken the current as reference and I have drawn the complete phasor diagram for the RL circuit. But usually the source what I am connecting, that I will be knowing, okay. Therefore, I can consider the analysis taking the voltage as reference. When the given voltage source you have taken as reference, we need to calculate the resulting current in the circuit. Therefore, I divide the voltage with the impedance Z. So, I know Z is equal to magnitude of Z at an angle of theta. Therefore, as per the slide what I have shown there, I is equals to V at an angle of 0 degrees divided by Z at an angle of theta. Now see, I have here a ratio of two complex numbers. V, of course, it has a angle of 0, therefore there is no imaginary part for this V, because sin 0 is 0. So this voltage will have only the real part there. But as in the denominator, because you have a magnitude as well as theta, I have here the complex term also involved in the denominator, okay. So this is what you have, a division of two complex numbers. So whenever you are using division of two complex numbers, it is convenient to have these complex numbers in the polar form. Why? Because I can simply divide the magnitudes V and Z and the angle what all you have, the numerator angle which is 0, denominator angle is theta, so there will be a minus sign between the two, which means that whatever angle we have in the denominator, it acts with the numerator angle with a negative sign. Suppose if the numerator also has an angle, it is not necessary that when I am taking the voltage as reference, it has to always have a 0 degree. There is some other reference with respect to that vector as reference, the voltage vector may have some angle. Let us say I have an angle of alpha here. So I will be getting V at an angle alpha divided by Z at an angle theta as the current expression. Then I can write the current magnitude will be V by Z, angle will be alpha minus theta. So the resultant angle is always difference of the numerator angle and the denominator angle. So if I have numerator angle as 0, I have 0 minus theta, therefore I can write V upon Z at an angle of minus theta. That is the current expression for a RL circuit when I take the voltage as reference. I will just retain this voltage triangle. I write here VL is equals to I times XL. I will come back to this equation. Now since I am taking the voltage as reference, the angle of voltage is 0. Now this is the RMS value of the voltage what I am applying to the source. The instantaneous value for this voltage can be written like this: V of t is equals to V maximum sine of omega t, because the voltage source what I considered is a sinusoidal voltage source. Therefore I write like this: Vm is the maximum value, RMS value will be maximum value divided by root 2, square root of 2 there. So current which has an RMS value of I will give you a maximum value of Im, I multiplied by square root of 2. Then it is also varying according to a sine curve, sine omega t, but it has a phase angle difference of theta degrees with respect to voltage. Therefore I write here omega t minus theta. This is what you have, the instantaneous current I. Okay. So therefore we can say, as per these equations, in a series RL circuit, the current always lags behind the voltage by an angle of theta, which is given by theta is equals to tan inverse XL divided by R, or it is tan inverse omega L upon R. For a given value of omega and R, okay, the angle theta depends on the value of L. Larger the value of inductance, that is more inductance, more will be the angle. Okay. Or you can also say the other way, if the circuit has a larger value of the resistance, theta will be smaller, current will be closer to the voltage axis. If theta is larger, current will be far away with the voltage vector. So this is what the expression for the current here. Of course, I have just given in terms of maximum value and all. On the slide, I have represented the maximum value of the current as a ratio of maximum value of the voltage to the magnitude of the impedance, and theta, of course, I substituted like tan inverse omega L by R in the slide. Okay. Now, I have a series RC circuit, but before going to the RC circuit, I like to tell one point using the voltage phasor diagram. From the voltage phasor diagram, I told you I can cut off these currents because all the three sides have a common term as current. Then I got the impedance triangle. Suppose if each side of this triangle, the voltage triangle, is being multiplied by the current I, already current term is there, but each side again I am multiplying by current I. So that will give us a new triangle. What you have here, IR multiplied by I, okay. So it becomes I square R. So you all know that I square R is the power in the resistor, okay. Then the height of the triangle, I have IXL, okay. I am multiplying again by I, therefore this becomes I square XL, or I can also write it as VL multiplied by I. On the base, I can also write this as VR multiplied by I. So the hypotenuse of this triangle, what you have, this is actually V is equals to IZ. Now I am multiplying this also with I because these two are getting multiplied. This becomes I square Z, or it becomes VI. See now, since all the three sides of the triangle are multiplied by the same parameter, only the sides will increase, but the angle will remain theta. There won't be any change in the angle. Now this triangle, because see I square R, it has a dimension of watt, okay. So each side represents the power in the respective components. Therefore, I call this triangle as the power triangle. It is a power triangle. This triangle, again I can write it as OAB here, okay. So this is a power triangle. So I have given you three triangles with the same letter representation OAB. First one is the voltage triangle where all the three sides represents voltage. Second one is the impedance triangle where base represents the resistance, height represents the inductive reactance, and the hypotenuse represents the impedance. Again all the three sides will have the same dimension as ohms in the impedance triangle. And in the power triangle, I call the base as I square R, okay. Now because the inductor will not consume any average power, I can call I square XL or VL into I as reactive power consumed by the circuit. What a component will consume the reactive power? Inductance. It is responsible for the reactance of the circuit. Therefore, this amount of power, it is consumed by the inductance. It is not the active power. It won't participate in anything, okay. It is only the reactive power, okay. So unless you have a reactive power in the circuit, the resistor also cannot consume any power there, okay. So that means in electrical engineering, if we say that if I want to transmit a real power to the transmission line, I need to have reactive power in the circuit. In the absence of reactive power, it is not possible for us to supply AC real power through the transmission circuit. Therefore, the inductance what all it consumes, that is called as a reactive power, and the product V into I, it appears as power, but it is not the real power. Therefore, I call it as apparent power. So Vi is equals to, we have, it is again a vector sum, therefore I will put right like this, I square R plus J I square XL also I can write here, okay. So this is the apparent power, this is the real power, this is the reactive power, okay. So that is the difference between, that is the total power in a single phase AC circuit, real power as well as reactive power, both combined together will give us apparent power, okay. Without reactive power, if it is a pure resistor, then only it is possible for me. That means when XL is equal to 0, I have apparent power is equal to real power. Otherwise, because of this, I will get a difference between the apparent power and real power. Okay. Now again, if I see here the right angle triangle, the power triangle, I can say cos theta, what I defined yesterday as the power factor, it is equals to I square R divided by VI. So I square R, which is the average power consumed by the resistor. Inductor will not consume any average power. Therefore, if I try to calculate the average power consumed by RL circuit, it is only equal to I square R. Okay. So that power which is equals to, I can write VI cos theta. So this equation will give you the difference between apparent power, real power and the power factor. Okay. So these two are related through the power factor. So power factor, it is the ratio of real power to the apparent power. This I have shown you yesterday. Now let us go to the RC circuit. I have a resistor R and a capacitor C. I represent the resistor by normal representation. Let us take the resistors as R, capacitor as C, and this combination, say I have connected to a voltage source of RMS value V volts. Okay. Now here also we have resistor and capacitor in series combination. Therefore, the current given by the source, which is I, passes through the resistor as IR, it also passes to the capacitor as IC and gives us the voltage drops VR across the resistor and VC across the capacitor. So that the Kirchhoff's voltage law will give you V is equals to VR plus VC. It is a vector addition. Okay, VR plus VC. Now the voltage drop across the resistor is I times R and the voltage drop across the capacitor is I times XC, right? Okay. So therefore, because this XC, it is negative in nature, I put minus J here, and J because this voltage drop will be along the negative vertical axis. Okay. I can also show this relationship taking the phasor diagrams for the individual elements. As I have drawn in the RL circuit, for RC circuit, I have the current as a reference and the voltage is VR will be in phase with the reference. That is, again you can say for pure resistor, voltage drop and the current in the resistor both will be in phase. When I take the capacitor, when I use this I as reference, okay, let me take the voltage as reference here, VC, the current will be leading by 90 degrees in a pure capacitor, IC. This is what I have done yesterday. I have shown you that current I of t is equal to maximum value of Im sin of omega t plus 90 for a pure capacitor. So taking that equation, I have drawn their voltage current relationship as phasor diagrams for the individual elements. Again here you see, I have the current as a common parameter. So to get a complete phasor diagram for this circuit, I need to draw these diagrams in such a way that the common reference or the common phasor, I should identify that as, I should take it as reference. Therefore, I take I is equal to IR is equal to IC as a common reference. Then now as per this, I have the voltage VR along the current, along current vector. Then if I want to take this IC along with IR, because IR is equal to IC, I need to rotate the phasor diagram for the capacitor in the counterclockwise direction by 90 degrees, sorry, clockwise direction, not counterclockwise, in the clockwise direction by 90, so that I will be getting the current vector IC like this and the voltage vector along the negative imaginary axis or the vertical axis. So, this is what we see. So, if I draw VC here, I will be getting VC this way. Therefore, adding these two, I will be getting the voltage triangle V here. So, this is the angle here now. I also still represent it by theta only, but the theta angle I will be measuring in the clockwise direction. So, this will give you the angle between the applied voltage and the current in the circuit. So, this gives us the power factor angle. Now, you can see here, if I draw the coordinate axis on this phasor diagram, my real axis is along the current vector, this is the origin, and the imaginary axis or the vertical axis, it is like this. Okay. Now, you can see for in the coordinate system, the voltage triangle for the RC circuit, it is in the fourth quadrant. Okay. For the RL circuit, I found this triangle in the first quadrant, whereas for RC circuit, the triangle will be in the fourth quadrant. Now, here if I take out the current as a common factor, I write here R minus J XC. So, I write again here I times Z. So, this Z, it is again the complex impedance, but this time the complex term in the impedance is because of the capacitor. So, this is what the phasor diagram I represented here. The voltage VC, VR is equal to IR, VC is equals to minus J IXC, V is equals to I multiplied by Z. Again I have an impedance triangle. Okay. So, in this case the impedance Z, I will write it as square root of R square plus XC square in magnitude, and angle of the impedance theta will be tan inverse minus XC divided by R. Okay. So, this are because of this minus XC minus value, the angle of the impedance comes to be negative. Now, remember when you have R and XC both together, theta, the angle what you have will be definitely negative, but always less than 90. Depending on the magnitude of XC, the angle theta will be closer to the 90 degrees. It cannot be 90 exactly, because when you have a resistance, but in the absence of resistance, I can say theta will be minus 90 for the pure capacitor circuit. Okay. Whenever R involves, theta will be definitely negative, but less than 90 degrees because of the presence of R. Okay. So, that you have to remember. Impedance angle for the RL series circuit is positive, always positive, and it will also be less than 90 because the resistance term is present, and in the RC circuit the theta will be always negative and will be less than 90 because of the presence of resistance R. So, blindly you can write down whenever there is a RC circuit, the angle will be negative. Okay. So, here also when I divide all the three sides of the voltage triangle, I will be getting an impedance triangle. Okay. As I told you, this voltage triangle or the impedance triangle or the power triangle, what all you get for this RC circuit will be always in the fourth quadrant. But power triangle, though I am representing as a triangle, each power what you have, it is a scalar parameter, it is not vector. Okay. Only for that identification of different powers, I am using this impedance, this voltage triangle as a reference or basis in writing down the power triangle. Okay. But all the powers are scalars, we cannot represent them by vectors. We have a complex power in a AC circuit. See, when I give a single phase AC circuit a voltage of magnitude V at an angle theta, the current resulting in the circuit can be written as the current I at an angle phi in an AC circuit. Okay. The value of the phi depends upon the circuit components, whether it is RL circuit or RC circuit. Based on that, the sign of the angle phi will be there. So, the power in the circuit is always given as V into I cos of the angle between voltage and current. Okay, the voltage difference, that is the power factor angle, right. Now I can also write down the waveforms for a RL circuit and RC circuit and draw the power curve for instantaneous power, and based on the power curve we can also derive and show that the average power consumed in a RL or RC circuit is VI times the power factor of the circuit. Okay. So far here today we just saw the behavior of RL and RC circuits in the single phase AC supply. Okay. So in the next session we will be doing the average expression for the power using the voltage and current power curves. Thank you.